Hello everyone, this is an introduction to gas stoichiometry. We've done stoichiometry before. Remember that you have to have a nice balanced equation for stoichiometry, and that for your upcoming exam you're going to need to use significant figures. So as you're going through your problems, I would suggest if you write everything down on paper, keeping to 3 decimal places. If you do everything on your calculator, just don't round until the end. Okay, and the video that I have for significant figures the link is posted in this PowerPoint. Just make sure you turn on closed captioning because for some reason the sound didn't come out very well in that video. Also in this PowerPoint is the significant figures decision map to help you if you need a little review. So these are your learning objectives. You need to be able to perform calculations using significant figures, like I just said. Be able to define the conditions for standard temperature and pressure. Be able to balance an equation. Be able to form stoichiometry calculations, be able to form stoichiometry calculations for gases at standard temperature and pressure, and be able to apply the gas laws to gas stoichiometry problems. Some of these are carryovers from things that you've done before, so some of these things like using significant figures, balancing an equation, and doing regular stoichiometry calculations should already be familiar for you. Also, at this point, we've done gas laws, so standard temperature and pressure should be at least a little bit familiar, so it's really the bottom two that are new. So this does look like a lot, but the new stuff are these last two objectives. Again, exam tips. There is a 10% margin of error built into Canvas, so make sure it's just to make sure that little tiny rounding differences don't make it to where your answer is wrong, but it's only 10%. So if you get a completely wrong answer, it's just going to be wrong. But just make sure, again, you're using significant figures and keep 3 decimal places all the way through to the end of the problem. Okay, so here's the link to the significant figures video, and here's that decision map. You can go through this on your own. And here are the conditions for standard temperature and pressure. This is also going to be a good way for you to know the conversion. So at standard temperature and pressure, if you memorize this, you're going to know how to convert, and millimeters of mercury has the same conversion factor as torr. Okay, 760 milliliters of mercury equals 760 torr. And if you're using standard temperature and pressure, chances are you'll be using ideal gas law. That's not necessarily the case all the time, but if you are using ideal gas law, remember that's PV equals nRT. And because your constant, which is R, is 0.0821 liters ATM over moles Kelvin, if you memorize those units, you'll know exactly what units you have to have for ideal gas law. Liters, ATM, moles, and Kelvin. Okay? So this next problem is just a review from gas laws to kind of get you into the mode of calculating that again. So here you have a standard temperature and pressure. So you have a temperature, you have a pressure, and it's asking you to find the volume of a gas, right? And then you have another volume, another pressure, and another temperature. So you have 3 total variables. So if you're using the 3 variables, temperature, pressure, and volume, and it doesn't mention moles, you're going to be using the combined gas law, which is P1 V1 over T1 equals P2 V2 over T2. You need to keep the standard temperature and pressure, the temperature and pressure and volume. These 3 things need to be either P1, the 1s or the 2s. You need to keep them together. So these 3 would either be 1 or 2, and the standard temperature and pressure that you're given will be 1 or 2. And your unknown volume is going to be with the standard temperature and pressure when you set up this formula. So pause the video, take a stab at it, and then I will go over the answer. So I'm assuming you've tried it. Okay. Now again, your unknown volume is going to be with the standard temperature and pressure. This is your standard pressure. You can keep the pressure at kilopascals because you're working with combined gas law. With combined gas law, the only thing you have to change is Kelvin. You always change into Kelvin, always, always, always. As long as your pressure units match, you can keep it at kilopascals for combined gas law. Okay, and because you put in milliliters, you're going to come out with milliliters. Okay. So another review problem. How many moles of neon gas are there if 25 liters of the gas are at 5 degrees Celsius with a pressure of 89.9 kilopascals? Because the problem mentions moles, we know that we need to use PV equals nRT. And remember, because R is your gas constant, 0.0821 liters ATM over moles Kelvin. Liters ATM, moles and Kelvin are the units you have to use here. Okay. And so after you've taken a stab at it, okay, you should have converted to ATM using this conversion factor here. Liters, you don't have to convert. You already have your constant, and you just needed to add 273 to that 5 degrees Celsius to get to Kelvin. Okay, so when you solve for this, you should get 0.97 moles. And so now that we've had a little review of gas laws, we're going to be looking at stoichiometry of gases. You need a balanced equation because it's like a recipe. If you have the wrong ratios in your recipe, your bread or whatever you're making is going to come out like crap. So you need a balanced equation because those coefficients represent moles. Okay, those coefficients represent moles. Okay, so this is from, if you're in my class, this is from Canvas, from quiz 4. Complete this statement: blank moles of N2 reacts with blank moles of H2 to produce blank moles of NH3. So remember, your coefficients represent moles. There's a 1 understood to be here, so it'd be 1 mole of N2 reacts with 3 moles of H2 to produce 2 moles of NH3. Okay. Now this is a regular stoichiometry problem, so this is still a little bit more review. Assuming an excess of hydrogen gas, how many grams of NH2, that should say NH3, NH3 are produced with 20 grams of N2. So this excess of hydrogen gas is actually important because this tells you, remember the idea of limiting reactants, right? The limiting reactant is what determines how much of a reaction yield you'll have, because you're going to run out of your limiting reactant first. It's like if you're making chocolate chip cookies, and let's simplify the recipe and say you just need chocolate chips and flour. If I only have 1 bag of chocolate chips and 10 bags of flour, I have to use the fact that I only have 1 bag of chocolate chips to determine how many cookies I make, right? Because at that point, if I run out of chocolate chips, they're not chocolate chip cookies anymore. So that's the idea of the limiting reactant. So if we have excess of hydrogen gas, it's like having the excess flour, right? So that's why they tell you excess of hydrogen gas to tell you what the limiting reactant is. And so you have to work with the 20 grams of N2 because they're telling you here that that is your limiting reactant. Okay. So you have to start off with your given, right? And you're given grams of N2. You're going to use the molar mass of N2 to get to moles of N2. And then you're going to use your balanced chemical equation to go from moles of N2 to moles of NH3. And then you're going to use the molar mass of NH3 to get to grams of NH3. Okay. And so you're given 20 grams of N2. And to find the molar mass of N2, you're going to take the mass of nitrogen from the periodic table. On my periodic table it says 14.007, and so you multiply that by 2. Remember, keep 3 decimal places. So I must have done this with a different periodic table, but it's fine. That's why there's that 10% margin of error. So N2 should be about 28, 14 times 2. Your balanced chemical equation says that you have 1 mole of N2 for every 2 moles of NH3. And nitrogen is about 14 plus 3 hydrogens, which is about 1, so you should get 17 point something. I'm not telling you to round, I'm just telling you to go through and make sure that your math makes sense. So 17.01031 should be around, that looks correct. Okay. So you have 20 times 2 times 17. I'll crack out my calculator to double check this. 20 times 2 times 17, 680 divided by 28. Alright, so my answer is going to be rounded to 24.1 because you have 3 significant figures here. Right? These zeros count because you have that decimal here. So trailing zeros count if there's a decimal. Leading zeros do not count even if there is a decimal. Okay? So if your answer was 24.2, 24.3, remember it's fine as long as you're within 10% of the answer. So now we're moving into gas stoichiometry. And what makes gas stoichiometry different? Well, because you're dealing with this unit of liters, sometimes you have to convert with liters, and because your balanced chemical equation tells you moles, there are times where at standard temperature and pressure we use this conversion factor, and if you're not at standard temperature and pressure, you're going to need to use ideal gas law to get the number of moles. And then once you get the number of moles, then you can start doing gas stoichiometry. So let me show you what I mean. So this problem says how many grams of water will be produced by 58.2 liters of CH4 at standard temperature and pressure, assuming excess of O2. So we know we need to do stoichiometry as opposed to just one equation because this is talking about a chemical reaction. Okay. This problem gives some more details. This is a combustion reaction, meaning that CH4 will combine with O2 to make carbon dioxide and water. Okay. So the first thing you're going to need to do here is write out a balanced equation. And because you're at standard temperature and pressure, this actually makes the problem a little bit easier because instead of plugging everything into the ideal gas law, you can just add this as your conversion factor. Okay. So this is our balanced chemical equation, and this is just a review of how to deal with combustion reactions because combustion reactions can be a little annoying to balance. So you want to fix the oxygens last. You would normally tackle the carbon first, but in this particular case you have one carbon on each side, so then you want to tackle your hydrogens. And so when you fix your hydrogens on this side and you put a 2 here, that makes this 4. And that changes our oxygens. Again, you want to change your oxygens last because generally there's something attached, oxygens attached to a couple different things. And so oxygen is going to change anyways. And so when I put a 2 here, that makes our total oxygens 4 because you have 2 on this side and 2 on this side. And so in order to make oxygens 4 on the reactant side, you put a 2 in front of the O2. Okay. Now if you get a combustion reaction where you have an odd number of oxygens, you're going to take all your coefficients and multiply them by 2. And I think we do a problem like that in the next video. There should also be a document within Canvas in the module that says balancing complex chemical equations. You might want to take a look at that just so you can have some practice with balancing combustion reactions. Okay. So now that we have our balanced chemical equation, we need to go from liters of CH4 to moles of CH4, and we're just going to use this particular excuse me, conversion factor to do that because we're at standard temperature and pressure. So, and then we're going to, after that is just regular stoichiometry. We're going to go from moles of CH4 to moles of H2O using the balanced chemical equation. We're going to go from moles of H2O to grams of H2O using the molar mass of water. And this is just a reminder to keep 3 decimal places until the end of the problem. Okay. So here, we're going to use that conversion factor. We have to get from liters to moles. So in 1 mole at standard temperature and pressure, there are 22.4 liters. At 1 mole at standard temperature and pressure, there are 22.4 liters. Okay. And so when we multiply that across, your liters are going to cancel and you're going to get moles of CH4. At this point, now it's just regular stoichiometry. You're going to go from moles of CH4 to moles of H2O using your balanced chemical equation. So these are your given moles that you calculated from liters. And this is from your balanced chemical equation. And you're going to get 5.196 moles of water. Okay. And then you use the molar mass of water to go from moles of water to grams of water. Now let's look to make sure that this makes the most sense. So oxygen's about 16, hydrogen's about 1, so if I calculate 18.0 something, that's about right. And so I'm talking that out because if you're in my class for spring of 2023, I definitely butchered one of these problems by having the wrong subscript, which changed the molar mass, which threw off the whole problem. So just go through and do what I didn't do and check your details. Okay, that was an example of what not to do. All right. So I used 3 decimal places throughout the problem, and so our original problem has 3 significant figures. So I have 3 significant figures at the end. Okay. So this is just an introduction. We will have another video, another lecture where we get into a little bit more complex, where we use the ideal gas law, but this is a good start. Okay, so if you need some review on how to do stoichiometry, there is a link in Canvas for a stoichiometry or a website that gives you a lot of chemistry quizzes, and that's not just good for stoichiometry, it's good for other things too. So if you feel like you're a little bit rusty on the things we went over at the beginning of general chemistry, feel free to take a look at that resource.